This video reviews the fundamentals of hypothesis testing. Hypothesis testing, also known as significance testing, involves comparing an obtained value for a parameter to an expected value. This testing assesses a hypothesis, or a statement, based on the observation or explanation of a phenomenon or problem. In discussing hypotheses, we typically talk about the alternative hypothesis, a statement based on the researcher's observation or explanation, and the null hypothesis. The null hypothesis and alternative hypothesis should be mutually exclusive, meaning they cannot overlap. That is to say, they cannot both be true at the same time. Additionally, the two hypotheses should include all possible outcomes. To make this concrete, I think WT students are more intelligent than the general population. I can write this as the mean IQ for a sample from WT will be greater than the population mean. I know the population mean is 100, so the mean for WT needs to be greater than 100 for this statement to be true. There are other possible outcomes though. The null hypothesis should address these outcomes. In this case, the other possible outcomes are that the average IQ at WT is less than or equal to 100. This statement represents a directional hypothesis or a one-tailed test. I'm asserting that one group will be higher on an attribute. In this case, I'm asserting that the WT sample will be higher than 100, will be higher than the population mean. A non-directional hypothesis, or a two-tailed test, suggests that a difference will be present, but does not assert a particular direction. So we expect the sample mean is different from the population mean, it's different from 100, but it could be more, or it could be less. To understand hypothesis testing, I first need to introduce the normal distribution and sampling distribution. The normal distribution is a theoretical distribution with scores symmetrically distributed above and below the mean, median, and mode. The mean, median, and mode are all equal and at the center of the distribution. Here we will see the distribution of scores from variable x. The mean of the population will be the most frequently occurring score. Here we see there are 8 scores at the mean. There will also be scores above the mean and below the mean. These scores will be symmetrically distributed around the mean, and it's this symmetrical shape of the distribution that makes it the normal distribution. You'll also hear it talked about as the bell-shaped curve. And so around the mean, what we will see is these symmetrically distributed scores with fewer and fewer scores occurring as you move away from the mean in both directions. The sampling distribution is created by repeatedly taking samples from the population. So here we have a population distribution with a mean of 100, and we will take 5 scores from this population in order to create a randomly selected sample. So the first score that we randomly select is x3 with a value of 100. We then select 4 more scores to create our first sample. We will then calculate a statistic. In this case, we're going to calculate a mean to represent that sample. So we add 102 for the second score, 98 for the third score, and so on until we have the total IQ for the sample, in this case 500. Then we divide by the number of scores in the sample, 5, and we get our first sample mean of 100. At this point, we're no longer concerned about the individual scores, x1 or x2. We're more concerned about the distribution of the sample means. And so this sampling distribution becomes the emphasis when we're doing hypothesis testing. In order to create the distribution, we're going to repeatedly take samples from that original population. And so we have the first sample mean here of 100. We go back, we randomly take 5 more scores, and we find that the mean for that random sample is slightly higher. This is largely due to sampling error. So when we go into the population, assuming that we don't make some type of error and have some kind of bias introduced, we're still going to see that our scores, our samples, may be higher or lower than the population mean. And so because of that, this distribution of the samples is going to have some variability to it. So the first sample is there, and then the second sample we go in, it has a slightly higher mean. The third sample we get is slightly lower. The fourth sample also happens to be right at the population mean. And so we repeatedly do this until we develop the sampling distribution, or a distribution of all these possible sample means. This distribution will center around the population mean when enough samples are drawn. So here we see the population mean was 100, so we should see that the majority of our sample means occur at that same level. And as we draw more samples, our sampling distribution will have a normal shape to it, meaning we should see the most frequently occurring score at the sample mean, and the sample mean should be symmetrically distributed around this point, again, due to sampling error, which occurs as some samples happen to have a lot of high scores and other samples happen to have a lot of low scores. Additionally, as we increase the number of samples drawn, the sample means will approach a normal distribution even if the original distribution was not normal. This is known as the central limit theorem. We then use this distribution, or more commonly estimates based on this distribution, as the basis for hypothesis testing. So we can evaluate if an obtained sample deviates from the population parameter. That is to say, is the sample mean we obtained likely based on this sampling distribution? We determine this likelihood using a previously established level of significance, which is also known as an alpha level, and the variability present within the sample means. Using these two factors, we establish cutoff scores based on our hypothesis. So if we want to know if our sample mean is significantly different from the population mean, our alternative hypothesis would be that the sample mean is not equal to 100. And if our alpha level is 0.05, we want to know that our obtained sample mean is outside of the range of the most commonly occurring sample means and would occur due to sampling error in less than 5% of the samples drawn from the population. We often determine the exact cutoff by estimating from our measures of variability, such as the variance and standard deviation. We use those measures to calculate the standard error of the mean, which is the square root of the variance divided by the number of scores in our sample. You can also calculate this variable using the standard deviation from the population and dividing by the number of scores in the sample. You can think of these estimates as representing the standard deviation of the sample means around the grand mean, or the mean of all the means. So if we added all these means together and then divided by the number of samples that we drew, we would obtain a mean of the means, right? An average of the means. And what we're doing is similar to what we did earlier when we were doing standard deviation, where we looked at the variability of individual scores around the mean. Here, though, we're looking at the variability of individual means around the grand mean. So if we use our alpha level of 0.05, then we can determine the cutoffs for our most likely sample means as 1.96 standard errors of the mean above or below the population mean. Now you may be curious where these numbers came from. there are charts, depending on if you're doing a z-test or a t-test or exactly which type of test you're doing. And somebody has basically already calculated the area or proportion of area under the curve and determined at what point do we see that there is only 5% of the area under the curve. So we have this alpha of 0.05. And here we see that we have a two-tailed test, or a non-directional test. So we want to take that 5%, that 0.05, and split it between the top of the distribution, the upper portion of the distribution, and the lower portion of the distribution. So we need 2.5% towards the top, 2.5% towards the bottom, and we could calculate this. We could calculate the area under the curve, but fortunately, for our purposes, we're not going to do that. We don't have to do that because it's already been done for us. And so based on that, we know that 1.96 is the cutoff in these circumstances. We should note this example only shows a two-tailed test, or a non-directional hypothesis. Our original hypothesis was that the WT sample would be higher than the population average, though. So we can ignore this two-tailed and focus on the one-tailed test. This change in our focus also means we can ignore the lower end of our distribution and focus the entire 5% on the upper portion of the distribution rather than splitting the 5%, as we were just discussing, between the top and the bottom of the distribution. This allows us to shift our cutoff. So the sample mean needed for significance is less extreme and only 1.65 standard errors of the mean away from the population mean. Similarly, this cutoff may change if an alternative alpha level is used. If we use a more conservative alpha level and shift from 0.05 to 0.01, our cutoff will be more conservative. As we now want to know that the obtained mean does not occur in 99% of the sample mean seen in the sampling distribution. This shifts our cutoff point so it is higher and more conservative. And so it now shifts to being positive 2.33 standard errors of the mean away from the population mean. This sampling distribution then provides the foundation for inferential statistics. So if a sample is extreme or rare compared to the cutoff, it is deemed significantly different from the population. But if it is found in this typical range of scores, relatively close to the population mean, we fail to reject the null hypothesis.